So in the last 3 days, we've covered different gas laws, and the gas laws were ways to calculate how pressure, volume, or temperature would change as gases would change. So I'll go over the 4 gas laws we learned, explain why they work, and we'll do one example problem. The first one was Boyle's law, and Boyle's law relates pressure and volume. We saw that the smaller a volume gets, the more pressure there is because the particles are hitting the walls more often. So there's more frequent collisions with the walls. So with this one, you can use any units you want. Just make sure that whatever units used for pressure on one side, it's the same unit on the other side. So your units have to be consistent, and we'll have to have the number of particles has to be constant. So like a closed container, a piston, or a balloon. And your temperature has to be constant. So, whoops, let's go for our example. I have a 2 liter. Liters is a way that I measure volume, so that'll be my V1. A 2 liter container of nitrogen gas has a pressure of 1.5 atms. 1.5 atmospheres is for pressure, like atmospheric pressure, so that'll be my P1. What is the new pressure of the system? So I'm looking for P2 is my question. I don't know it. What is the new pressure of the system if the volume is increased to 4.5 liters? Okay, so there's my V2. All right, so I can see there's 2 P's, there's 2 V's. Even if I didn't have the equation on the slide before, I'd know that I'm going to use P1 V1 equals P2 V2. I'm trying to solve for P2, so P2 has to be alone. Right now it's being multiplied by V2, so to get it by itself, I'm going to divide both sides by V2. That'll undo the multiplication. Okay, so then that means V2 divided by V2 is 1, so V2 is gone, and I'm left with just plain old P2 by itself. Okay, so then I can plug everything in, and I've got 2 liters times 1.5 atms, atmospheres, all divided by 4.5 liters. So when you type that in, you'll go 2 times 1.5 is 3. 3 divided by the 4.5, and you'll get 0.67, or about 2/3. And the units for that, liters cancels out. My units are atmospheres. Okay, so that's our first example. Charles' law was the next one, and that was all about volume and temperature. So this time, N for the number of particles is constant, and pressure has to be constant. We'll have to be careful and just use Kelvin this time. So, let's see. We have a 500 milliliter balloon. It's cooled with liquid nitrogen from a temperature of 298 to a new temperature of 78. Okay, so 500 milliliters, that's a volume. And it's that volume when it's this temperature, so that'll be T1. This will be my T2, and it's asking for my V2. Okay, so I've got 2 T's, I've got 2 V's, so I know the equation I'm going to use will be V1 over T1 equals V2 over T2. So first you write the equation, then you can substitute the numbers in or rearrange first, whichever you prefer. If you like to cross multiply and divide, that's totally fine. Just plug it in, go ahead and do your thing. I'll use algebra. So I'm solving for V2. I have to get V2 by itself. So I'll undo this division by multiplying. I'll multiply both sides by T2. Okay, so T2 divided by T2, it's gone. V2 is by itself. So that means V2 is equal to that second temperature, that was 78 Kelvin, times the first volume, that's 500 milliliters, all divided by the initial temperature, which was 298 Kelvin. And I remember doing that one, and it was 130 milliliters. And it makes sense, because the temperature is getting lower, particles are pushing less, so they're pushing the walls of the container out less. So as the particles slow down, the volume gets smaller. And let's see. Next one, we had Gay-Lussac, so this is pressure and temperature. As temperature increases, particles move faster, they end up hitting the walls of the container more frequently, and they're hitting harder, so pressure is higher. So for this one, number of particles is constant, your volume has to be constant for this to work, and your temperature has to be in Kelvin. So, here we go. I have, let's see, sample of gas in a closed container has an initial pressure, so there's P1, 1.4 atmospheres, at 264 Kelvin, so that's T1. The gas is heated to a temperature of 298, so that's T2. What is the new pressure of the system? So that's going to be P2. So we're looking for P2. So right there I can see I've got two P's, two T's. It tells me which of my four equations to use. The ones with P1 over T1 equals P2 over T2. All right, and I'm looking for P, so I have to get it by itself. So I'm going to undo what's being done to it. I'm going to multiply both sides by T2. So times T2 and times T2. Okay, so that's gone. P2 is by itself, so now I can just plug in these three things. So T2 is 298 Kelvin times P1, let's see, that was 1.4 for ATM, divided by T1, so 264. Okay, switched rooms and I left my calculator in the other room, but let's see. The temperature is increasing, so the pressure increases, and we did a bunch of these, so I'm pretty sure it's 1.6. Ooh, thank you. Hey, nice. We have a calculator. So I'll go 298 times 1.4, enter, divided by 264. All right. 1.58, so that'll be, round that to 1.6, and let's see, Kelvin cancels out to unit of atmospheres. Excellent. Last one. The last one is the combined gas law, and so this puts all of our variables together. It's a closed container, so N's going to be constant, and everything else can change. So if you see two P's, two V's, a T, and you're asked for a second T, you're going to use this one. By the way, if you're solving for the bottom thing, you can flip this whole equation and it'll still work. You can flip it and say T1 over P1V1 is equal to T2 over P2V2. And that works for all of them. If you flip them, they're still equal. Okay, so let's try this one. Let's see. The child has a toy balloon with a volume of, so that's volume V1, 1.8 liters. The temperature of the balloon when it was filled was 20 Celsius. It's Celsius, we'll have to turn it to Kelvin, convert it to Kelvin, so we'll have to add 273. So that's my T2. And the pressure was 1 atmosphere, so that's P1. Okay. If the child were to let go of the balloon and it rose to 3 kilometers, that's not a pressure, a temperature, or a volume, so it's not going to go in this one. You could label it as distance if you wanted. Here's a pressure of 0.667, so there's P2. And the temperature, 2, is negative 10 Celsius, so we'll turn that to Kelvin. And they're asking what is the new volume, so we're looking for V2. Okay, so I have 2 P's, 2 T's, 1 V, and I'm asked for the second V. So I know what equation I'm going to use. It's P1V1 over T1 equals P2V2 over T2. All right, and I'm trying to get V2, so I have to undo what's being done to V2 to get it by itself. So right now it's being multiplied by P2. Let's divide by P2. And I'll do that to both sides, divide by P2. It's being divided by T2, so let's multiply by T2 and multiply by T2. Okay, so the P2s are canceled out, the T2s are canceled out, and V2 is by itself now. Okay, so I've got these 5 variables. I just plug them in and multiply, and we'll see what we have. So for T2, here, I'm going to put it over here now. V2 is equal to, so T2, second temperature, that's negative 10 degrees Celsius. We add 273 to get 263 Kelvin, right? Celsius plus 273 is our Kelvin. P1, that was 1 atmosphere, so 1 ATM. V1, that was 1.8 liters, so 1.8 liters, divided by, I've got P2, P2 is 0.667, 0.667 ATM, and let's see, it's divided by T1, and T1 was 20 Celsius, so 20 plus 273 to make it Kelvin, 293 Kelvin. Okay, now we have to type all that in. We'll multiply the first three numbers and then divide by each of the things on the bottom. Make sure you try this one. This is the one that kids make the most mistakes on in typing it in. So 263 times 1 times 1.8. I hit enter. Divide by 0.667. Enter. Divide by 293. You can also use parentheses, but it works this way as well. And I got 2.4. So the volume, V2, is 2.4 liters is what you should get. So make sure you actually type things in and you can get it right.